In this video, we're going to be covering how to schedule different things. So this is essentially the baseline, the most simple way of establishing an operating system. So what we've done thus far is we've just put things in infinite non-reactionary loops, so it's just going to continuously print things over and over and over, or flashlights or whatever. But ultimately, for a real-time flight system, what we need to be able to do is actually react to things and have decisions made, etc., constantly reevaluated over time. So what we're going to do here today is we're going to place these tasks. So when I refer to a task, what I'm saying essentially is accomplish something using your computer. So that's kind of how operating systems work, is it has a bunch of different what are known as tasks in it. So the task of, in this case, flashing the light, or the task of firing information from your board to your computer. And what we do then is we schedule these tasks in a predictable fashion. So we say, do this task, then that, then this. So we have all these predefined orders of things. But then we also have priorities built into those tasks. So for instance, if we're running a priority 2 task, and then all of a sudden, let's say behind that priority 2 task is another priority 2 task. So that is the next one up in the queue. And let's say suddenly a priority 10 task, so let's say that's our top priority, suddenly shows up. What will happen is that priority 10 task will butt to the start of the line, so that way it can be executed more urgently if that's necessary. So that's why that real-time evaluation is so crucial for us. So fortunately, we don't need to use any Halcogen today because we're not changing any of the actual abstraction layer or any of the interfacing with the board. We're just going to mess around with this code inside. So the first thing I'm going to do here is let's go ahead and delete that infinite while loop, because again, we're not going to be using that for this instance because we're actually going to officially schedule our tasks. And yeah, that's about it. We're going to leave the for loop for now. We can get rid of that later. So let's go up to our header files and let's start adding the things we're going to need. So because I have a very bad memory, I'm going to go into, again, a previously established code, and I'm going to add in the ones we need. So the ones we're going to need today are actually just OS task. I'm going to add these other 2 in as well, just for purposes of this demonstration's the future, because you're probably going to continue to use this as we're going to develop more complex operating systems. So all you need today is OS task, because all we're doing is creating tasks and running them. In the future, we're going to actually create the queue that stores those tasks, so it has an actual execution order rather than just us predefining it, so it's a little smarter essentially. And then eventually we'll also have a timer, so it's keeping track of everything. So now that we've included those header files we need, what we're going to do is we're going to start adding code. So let's start by creating a task. That's probably a good place to start. So if I go over to this, again, predefined code, what I'm going to steal here, is, yeah, let's just steal this one. So I'm just stealing a task framework I've already written, so we don't have, I can just go through and explain step by step what we're doing here. So we're going to place our tasks within user code begin 2. Don't have to place it there necessarily, but it's a good place to have it nice and separate from your main code. And I'm going to delete just this for loop. This is just doing something else, so don't worry about what was inside of this task. I just keep in mind that I'm just using this as a framework for this new task I'm creating. So we're going to create vtask1, and just for the sake of this demonstration, might as well create vtask2. Okay, so all I've done here is I've created these objects, or these functions known as tasks. So inside of these, we're going to contain functional code. So in this case, this one we'll say is our flashing light code, and this one is our psi sending code. So essentially, these are separate predefined actions we want the computer to be able to take. So what we can do then is we can, within our main, we can schedule them in a fashion where we say, okay, execute this at this time when we want it to. Rather than just having to organize everything in here, we can specifically call these tasks from main in a more scheduled fashion. So vtask1, as I mentioned, is that GIO. So what I'm going to do is I'm going to rip this GIO set bit code and dump it into this task. So this has ultimately not changed anything in terms of what it's accomplishing. I've just moved it from main, where it's running over and over again, into a task that we can call. That's all that's happening here. And for task 2, we're going to do a similar thing. We're going to slice end. Great. Okay. So these are essentially our 2 tasks. Again, nothing has changed in terms of what's functioning on the code itself. However, what's happened now is we're going to be calling these tasks to use them in a more controlled fashion. Now I can get rid of that delay loop, and just to explain why. So the delay loop, again, was just wasting the computer's time. So that way, as it changed the bit to flash that LED, what would happen normally is if you just had it changing without any delay code, it's just going to change at whatever your processor is clocked at, so an extremely fast rate. So you're likely not be able to see those flips over and over again. So to slow it down, we just put in a big long for loop that the computer would have to count to, so that way we would be able to see the light flash at a much slower rate. So for that, what we've done now instead to replace that is a free RTOS built-in function known as vtaskDelay. So it's essentially the same thing. It just delays the task in, I believe, milliseconds. If you take a look at the documentation online, you'll be able to know for sure. But I'm going to go off the fact that it's milliseconds today. So I'm going to set it as 1,000, so it blinks every second, or hopefully every second. So now that we've set up these 2 functions, again, this accomplishes what we had before, just in a different fashion, in a more controlled fashion. What we need to do now, though, is actually set up the framework in main to be calling these tasks at whatever controlled rate we want. So we're going to leave GIO in it and Psi in it, because again, we do want to initialize those protocols ahead of time so the computer knows what to use. Just now we need to write some code in here to deal with the actual tasks. So there's a few different bits and pieces we need to keep track of here. The first is, where are we? Right. Rip a little more code here. Again, don't worry. I know there's a lot of volume to some of the code you're seeing here. I'm going to go through everything step by step so you understand it. And there's our init. Right, we want to start the scheduler. And one more thing. I'm going to go up here. Yeah. I'm going to add these task handles. Okay, so as I mentioned in the first video, we typically place constant global variables, things like that, within user code begin 0. So I'm going to place those there. So let's go through. I've added 3 major things here. Let's just talk about them. First is X task handles. The second are the task creation functions, and then the third is the task scheduler itself. So let's start with our X task handles. These ones are nice and basic. These are essentially just pointers pointing to the object of a task handle. So what that means essentially is each task handle points to an individual pre-existing task. So this is the pointer we're going to use to point to that task. So when we say, okay, X task 1 handle activate within our code, what that's going to do then is utilize that pointer, which points to our, let's see what it's associated with. So as you can see here, X task handle 1 is associated with task 1, which is expected. So it's going to use that as a pointer to point to task 1 and then go inside of it with the parameter we provided it and execute the code. So again, these are just pointers to those functions. So these are just things you need to have if you want to utilize tasks and be able to point to them, which you're going to want to do. So you could have a whole lot of these eventually. We just need 2 for today because of the Psi and the GIO tasks. Okay. Now let's talk about X task create. The indentation is a little weird here. I'm trying to make it look a little nicer on the eyes. There we go. Okay, is that? No, doesn't matter. It's good practice to keep your code as clean as possible because you're going to get overwhelmed pretty quick with all the there's a lot of volume associated with coding in FreeRTOS. As you can see here, a lot of the pre-established functions there's a lot of parameters and things like that. So keep your code as organized as you can because you're going to lose track of where you are and what you're doing pretty quickly otherwise. Okay, so again, if I haven't mentioned this, like the xtask create, the xtask create handle, all these things we're adding here, so these special functions, they're the things that are predefined either within FreeRTOS.h, so the FreeRTOS framework we're using, or within the Halcogen code you generated. So all these things are not functions that we've had to slave over to create. They're just things that already exist that we're now using to our benefit. So why does that look like? I think I have one too many brackets here, so I'm doing this. Should have looked at this before I made this video. Okay, so cross our fingers here that this will work. Let's just go through the second step. So again, all I brought up before was the pointer itself to the task creation. Now we're going to go through within main the process of creating a task. So that is going to be accomplished, as you can see here, with xtask create. So what this is saying is, let's ignore the if statement for now. Let's just look at the contents inside. So xtask create takes a bunch of different parameters. The first is the task it refers to itself. The second is the handle of the task. So if you want to ever know what task is running, and you pull your FreeRTOS function and say, hey, what tasks are you executing right now? These strings that you insert, so I can put really anything in here. I could put hello world or whatever I wanted. That's going to be what it returns, so it tells you what it's running. This is the amount of size associated, or allocated, I should say, to the task. So we're going to go a lot more into depth later in terms of memory allocation, because on such small boards, how much space we give to tasks, because obviously tasks can eat up space pretty quickly, is pretty important. So this is just the amount of space we're saying, okay, this is what you can potentially use. So config minimal stack size is just another predefined FreeRTOS.h size. So that's just what we use for now. Once you're actually working on flight code and things like that, you'll be affecting or changing that number to things that actually suit your purposes. But this is just a good one for now. And then a few other parameters, which you can take a look at online if you're curious about. And then finally, just a pointer to the task creation itself. So just one other note is within this if statement itself, the only reason we didn't just write xtask create and that's it is because we don't want to be creating tasks on top of themselves, because obviously you want to, at this point we're not worried about multi-threading or anything like that, so we're just going to be executing one task at a time. So what all I've said here is if this task does not exist, then run it is essentially what we're going at there. So just place that all within that if statement. All this code will be available to you on our GitLab. It'll be linked in the YouTube description as well. So if you just need to rip this off, feel free. And then in terms of understanding every parameter, if you're really curious about what each of these things mean, because in the long run you will be working more and more with each of these different parameters. For now, it's not really that important other than task names. And then all I said in here is while one. So if the task could not be created, so if we had some form of failure, what we want to do is we just want to place it in an infinite while loop just to hold it off for now, so nothing is broken. So not something you would do in flight code, but in this case it's just an easy way of saying this didn't work. So we could have written return 0, or like have a print statement that says creation didn't work and then return 0, whatever. Just for now it's just a while loop. If I were you, I would just do a return 0, but 6 of one, half dozen of another, because for this simple use case, it's going to be created no matter what, because nothing can really go wrong with such a simple setup. Okay, moving on to task creation 2, exactly the same thing. It's just now we're using vtask2, task2, and the task2 handle. Other than that, the exact same code. Then the last thing we're going to do here is vtask start scheduler, and I just want to touch on this quickly. Obviously, it should be pretty obvious what this does. Essentially, this just says, okay, you've established a scheduler, so you have tasks, and you have tasks you want to schedule, and you have a schedule that will contain those tasks and schedule them accordingly. now actually enter that scheduler and start using it. So the reason the placement of this is so important, so you'll notice it's right at the bottom of our main, is because essentially once you enter that scheduler, you can't get out of it. So this is important because if you have not already established your scheduler ahead of time, it's not going to have any information to work with. So if we wrote vtask start scheduler ahead of all this code, even your SCI in it or your GIO in it, so this stuff here, it will never hit that code in main. This immediately enters the scheduler and it just stays there forever until you terminate the program, essentially. So that's why it's so important to write all this other code above it, so that way once we enter the schedule, all our setup is already done and it has all the information it needs to run its code. So what we've done now essentially is we have actually scheduled our tasks. So what should happen, but I haven't messed anything up in particular, is let's build this code and see if I've broken anything off the top of that. Okay, so I've broken a few things. What have I done wrong here? So it doesn't know what X task handle is. So my immediate thought is, oh, I must have not included an appropriate header file. Let's just see. So what I'm going to do here is I'm just going to swap out the header files in a program I know works. Let's see if this fixes it. No luck. Okay. Try something else. There we go. No errors. Okay. This was my mistake. I misspoke earlier, so if you had it set in your head with this, try to get it out of your head. You want your include files to be above your X task handle. This is a stupid mistake on my part. I should have realized this. Because X task handle is a predefined object that exists within freertos.h, you need your code to have the freertos.h ahead of your X task handle, because your code needs to search the header file so it knows that that exists before trying to actually access it. So just a dumb mistake on my part. You should probably consider, actually I'll just do this right now. So I'm just going to move all these header files up into 0, because that makes a little more sense now that I think about it, because obviously you want those to be accessed first. Let's click save and build, and hopefully this, yeah, so this now builds, yeah, problem free. So that's great. And now what we're going to do is we're going to flash this code, and provided I didn't mess anything up huge, we should essentially see the exact same thing going on. Now, because I used a different task delayer, there's one thing I actually just thought of, which is that if you recall, or if you happen to notice when I was doing this earlier, I went into, when I created these tasks here, I put a task delay in 1, but I didn't put it in 2, because what I forgot, and this is what I messed up here, is what I have right now essentially is I've created tasks where there's not going to be any delay, which means that, yeah, there's a few things I forgot here, which is fine. So this is good learning experience just in general. The nice thing with what we work with is FreeRTOS has all these beautiful predefined functions that are easy to work with, but the problem is there's just a huge sheer volume of them, so it's pretty easy to forget little things here and there, which I've definitely done this time. So I'm just going to go over with you guys quickly the mistakes I just realized I made before I even ran the code. So the first one is a task delay. So I added a task delay to the light blink, which is great. I didn't add one to I'm adding one right now, and that is simply so when it executes, there's enough of a delay before it executes again that I can actually pick it up visually. So that's the idea behind that. The other thing I'm going to do here is I'm actually going to chuck a while loop inside of this task. So why am I doing this? I'm doing this largely because this is just a training exercise. For future reference, you're not going to be putting infinite while loops likely anywhere. However, for this case, the reason I'm doing this is because I'm just showing you how tasks work. So in a more typical use case, what's going to happen is you might have a while loop on the outside of these, so it keeps running them over and over again. But you want things to be able to react inside. So maybe don't always run task 1 or don't always run task 2, depending on the scenario. Now, for our purposes, we just want these to be running perpetually, just like our last example. So for what I've done here, essentially what's going to happen now is when we execute the code, it's going to enter main, read all those header files, create those tasks. And then when it starts the scheduler, it's going to create task 1 and task 2. And then it's just going to be stuck in this while loop for the rest until I remove the power again, because in this case, I'm just trying to show you guys how to move things into tasks. For future, we're going to be actually reacting to these things and calling the tasks when we want to, rather than just calling them or calling it once and then being stuck in it forever and ever and ever. But for this case, that's not a big deal. So we've just migrated essentially our code from the last lesson into this one, into these new tasks. So we have an infinite while loop, as well as our GIO code to flash that light, and a little bit of a delay there so we can see the flash. And then the same thing for the sysend to send that string. So I'm going to resave and build, and at this point, with my human knowledge, I'm feeling fairly confident this is going to be good. All right, let's start playing this. And here you go. Okay, so again, can't show you the lights because I don't have a camera, but the LED is flashing at that rate of approximately I think it must be milliseconds because it's looking like it's flashing at one time per second. So the LED is flashing at a slower rate because I slowed it down relative to that for loop we were using initially to delay. And then you see here the UVSD, which is actually flashing at the exact same rate. Has been populating as well, so we're continuing to get information through this. It's just a bit slower of a rate, so you should see it show up in a little while here. So yeah, that's going to conclude today's lesson. We've essentially now put our information within a scheduler. Yeah, there's another one. We've migrated that GIO code and that sysend code into a scheduler, and with that you essentially have the three main principles of UVSD software programming, which are sending information to a board, using the board, and using the board with that, sending information from the board back to your computer, and now actually putting that stuff in a scheduled, controlled, operating system-ish manner. So that's going to conclude our 3 intro lessons. Hopefully this was relatively clear. I've gone through this quite a few times with different people, so hopefully I've done an okay job of explaining things. If this is your first time, if you're new, you never even talked to me, do feel comfortable to ask me any questions you have or give me feedback, criticism, whatever you'd like about what I've talked about. And yeah, again, GitLab should be your ultimate resource for learning about what we do here. So we have within the software repo, so Orcasat, OBC software, we have a reading list with a bunch of hardware in there and software readings, an initial README for getting started, meeting notes that keep track of what we've chatted about in previous meetings, different architectures for our software, things like that. So there's a huge resource here. Another really valuable one are the Texas Instruments TI forums. They answer tons and tons of good questions about their processors and chips and dev boards and things like that, so that's very useful. And last but not least, as I mentioned before, is don't be afraid to use the human component and ask us any questions you have. So yeah, hopefully you enjoyed, hopefully this was clear, and yeah, hopefully I'll be seeing you at a meeting soon with your new knowledge about how to do this.